So in summary, my name is Francesco Mikulis-Borsoi. I'm a current senior computer science major at UNH. And what I'm going to be talking about today, I'm pretty sure I'm sharing my screen, okay, perfect. Landing throttleable hybrid rockets with hierarchical reinforcement learning in a simulated environment. It's a bit of a mouthful, but the project started at the start of the year when I had to choose my thesis because I'm going to be graduating with honors. And so I needed to do some work on my own. And I was able to re-leverage a 950 course, a graduate seminar for advanced reinforcement learning with Dr. Petrick. And yeah, so it all started from there. Markov decision processes are, I believe everyone's heard of them, but they allow to model decisions in discrete stochastic and sequential environments. And so in layman's terms, their next state is independent of the past given your present state. A hierarchical structure involves multiple layers where you have someone that's more important and that has a critical decision at the first step that will then feed information such as an action, which will then be part of a state of another MDP at a very layered approach to then explain and be able to have a very simple model of a complex controller. This is a problem that is actually difficult and pretty interesting because trying to land a rocket is a continuous and partially observable state space because you can't really store all the state variables or else you would explode with your state space size. Also, and we did pose a requirement of real-time control, so a lot of the search algorithms wouldn't have worked to do something like this, especially if you're going to do it on board on a small model rocket. So the objective of the project was to land this throttleable hybrid rocket with thrust vectoring from varying initial states. The controller has to be very small, and so this MDPs are perfect for this because if you have a state action value table, you can just look up your state and then you'll find the actions that's going to be the best for you to take in that moment. There is no visualization for this tool because I started working with OpenRocket, which is an open source simulator in Java. And there's no visualization to have a 3D idea of what was going on. The objective was to land the rocket with a vertical velocity of 2 meters per second or under 2 meters per second and a zenith angle less than 8 degrees from varying initial states around 30 meters of altitude starting from negative 10 meters per second within 8 seconds. So there were a lot of constraints. We're going from about 30 meters to 0, from negative 10 to sub 2 optimally, and then keeping that zenith angle pretty good so that we could actually have a landing. So this is the first picture up here is the traditional reinforcement learning state action approach where the agent has an action, behaves on the environment, gets a reward, and then transitions to another state. And so the idea is that there was an algorithm in Java that would speak with OpenRocket, and then it would send over data using UDP. And then in Blender with a Python custom script, we would actually be able to visualize that information. I do have a picture. I have a little video on my phone, like a 20-second video, which I could flip.
Oh, cool.
Be interested in looking at that.
Yeah.
But the main components of this project are that it's using a hierarchical structure, as in there are 2 main MDPs. One of them is called a lander. One of them is called a stabilizer. The lander is kind of the master. It selects the thrust and it feeds it to the state definition of the stabilizer. So the lander has angles, log2 position, log2 velocity, and it selects the thrust based on these conditions. And then thrust gets used in the state of the stabilizer with time. And the stabilizer MDP that was crafted very carefully because the inputs and outputs are axis independent. This means that you have complete symmetry and you can reuse the MDP in both of the axes. That actually reduces the state space by the square root and it's really, really effective for learning purposes, and it drastically increases learning rates, which is what we saw. I'm going to go over a couple of the graphs So one of them, this graph here is, I labeled it as 90% success after 1,000 episodes. So after about episode 1,000, the average of all the data points is about 90% success. So we can see a pretty fast learning rate. This was with about an exploration rate of still 3%. There are about 100 states for both the different MDPs. So 3% would mean that about 3 were completely random actions. And so getting 90% is pretty good. Another cool thing is this is the Blender visualizer that I was speaking about. So it sends information over directly over UDP, and it's able to real-time process. Now, the nice thing about using UDP is it doesn't have to be on your computer. It can be on another computer on the network, and you can visualize the whole thing. And I can actually play that on my phone for a second. And this was another simple graph. I think I need to keep it in proportion of this one, but with a lower exploration, there was much less oscillate. It was oscillating a lot. The value function was oscillating a lot less for how it was succeeding. But that's another one, and I do hope that this will be good enough. Okay. Please forgive me, I don't have the most up-to-date visualization code that I was able to get a video of working, but let's see if this can be seen. It's pretty slow, so but this is very slowed down about 20 times, I think. But the idea is it's able to slow it down and go in vertical, even though it wasn't at the start. So the idea was to use random initial starts for both velocities, altitudes, orientations, and angle velocities. So yeah, that was the key part of the project. This is a contribution to reinforcement learning because it's a standard framework. Technically, it's been, I don't even know, multiple hundreds of hours working on this, where hopefully it will be, I'm going to be able to get this released as part of my thesis and people will actually try it out. I spent a lot of time trying to define a schema for an MDP. So schemas actually have a state definition, have an action definition, and the nice thing is you can put boundaries, so min, max, and precision on that. But also I wrote a custom formula evaluator where you can type in a mathematical formula. I did it without pluses and minuses, but it has variables as well. And so you can do kind of anything. It will automatically pull it from the MDP state or action definition and then evaluate that. So you can define your own log scale, for example, using a simple formula. And there's a lot of software development and the implementation of multiple RL methods. There was Monte Carlo, TD0, and then SARSA. And then the rewards can be specified in the schema. So by just giving a user very simple interface where they can just put in a JSON file, that's kind of the idea, is you can run it and you can see how you're going to perform. Also, there's major plotting capabilities now that were not there before. That as in plotting the actual states of the MDP, not the actual simulation values for the rocket, which is very useful for debugging. The non-hierarchical version of this discretization was succeeding at under 10% after about an hour of training, and so I didn't even put it on the plot because it was just a flat line. But yeah, it's doing this hierarchically drastically changed the outcome and reduced the state space. So that was pretty effective. I'm gonna wrap up fast. Yeah, the idea of the 3D visualizer is it integrates OpenRocket with Blender. It's also a general nice request from the OpenRocket community. And with the visualization extension, the approach demonstrates that these hierarchical MDPs are pretty effective at reducing that state space, and that the nice thing about having them split is that you can define a very specific state space discretization based on their objective. And so, for example, the stabilizer really wants to stay vertical, so it can have a pretty reduced angle, but then with a log scale, that makes a lot of sense, whereas it doesn't necessarily always make sense for the other MDP of the lander. for the lander was a Monte Carlo with a terminal reward of negative absolute value of the velocity, which is pretty straightforward. And the stabilizer was negative angle squared plus 1 because it was using positive rewards with TD only for a certain amount, but as soon as it got there, it would always try to follow that policy. Splitting these again gave a meaningful reward function. So after the whole semester, there's been about 169 commits to this fork of OpenRocket, over 10,000 lines of code that went in there. I'm still trying to finalize for the thesis to add a reacher MDP that will be able to drive the rocket to a specific landing pad position, XY, on the grid. And the next steps are, continue investigating this hierarchical MDP formulation and potentially add a toolbox for OpenAI Gym. And then go for this benchmark. I hope I did not speak too much.
No, you did a good job.
Right on target. So obviously all of this is in simulation. Have you conjectured what it might take to move from simulation to a practical implementation?
I've looked into a lot of that, and for one point in time, I think at the start of the semester, I was overconfident that that was going to be possible. Now, unfortunately, once you have a hybrid thrust, because the thrust has to be hybrid for you to be able to level it. Once you have a hybrid thrust and you have a gimbal, you're a missile. So that's just, as soon as you have those two, that's it. So the only way you could actually do it at home is without using hybrid. So you go 100%, but that's more of a guess. It's not really, you're not guaranteed that you're going to get a success, and there's too much noise to be able to do that. So unfortunately, I got my hopes down. Also, commercially, they're not available for a lot of good reasons. Because having a gimbal and being able to direct a rocket, it gets very difficult. But this is landing up right very slowly. So there's no damage. There's potential for getting out there. OpenRocket claims about a 90% accuracy with the real world for after a certain amount of test model launches that the open source community, that the rocketry community has done with OpenRocket for altitudes, like 90% on the max altitude and 90% on the max velocity. And so it's pretty good, but I wouldn't trust it faithfully for this specific approach, because there's probably a lot more wind impacting you when you're coming down for those last few meters, and there's wind components in there. There's randomization for all of that. They have all the roll rates. They have a lot of very good air coefficients, but I still wouldn't fully trust it. I would want to try it, and if I could build a reusable hybrid rocket for $100, maybe with $5,000, I could figure it out after breaking a few.
There's a limit to how much you can afford to make errors, right?
And the other issue is they're not $100. For example, SEDS, I spoke with them a certain amount and collaborated a little bit during the semester, but they just built their own hybrid engine, and their own hybrid engine was 10 grand. So it's it's a big engine, but it gets very expensive very fast.
It's not like an Estes engine that you just go pick up at the hobby shop. Yeah,
I wish. That's what I was looking for. I thought I found one. That's why I was so happy.
So what was the aha moment?
The aha as in it works?
No, you've done a lot of work here. Was there one thing that's kind of stood out, your aha moment in terms of your research and your findings?
That's a good question. I think the aha moment was, so last semester, there was no symmetry on that stabilizer MDP. I was just trying to do a single MDP and then try to split it, and it was a little iffy. But this semester, I focused on getting this part to work. But so the aha moment was when I trained it in 2-dimensional, only on the X, and so only vertical and on the X-axis. And I executed the policy and trained it, ran it, 1,000 simulations, and it was doing okay. And then I was like, okay, I'm going to switch the axes to Y. If now it works perfectly, then it's symmetric and it works. And it did. And it behaved exactly the same as the x-axis. And that was huge because I was like hoping it was going to work. And I ended up having to do that. I forget, I think it's like angle velocity x is negative of the actual angle velocity y. And then like the y is like the positive x because of the coordinates flip. And if you don't have your coordinates flipped correctly, if one of the signs is flipped, but everything else is right, then your whole thing is going to break. So seeing that happen on the x-axis and then on the y-axis was the policy following through was very interesting.
Fantastic.
Do you have an idea of what the real frame rate would be or what your simulated frame rate was?
I was doing about 50, I was doing a time step every 10 milliseconds, either 10 or 20 milliseconds. I'm just saying 50, but that's not the case. I was doing a time step every 10 or 20 milliseconds. And then if you're in the same, so simulated 20 milliseconds is a step. If you're in the same state, then you just keep simulating until one of the MDPs is going to be in a new state. So it was pretty low. The built-in OpenRocket has a RK4 simulation parameter approach, which is apparently very known in control, which I have no idea, but it does numerical integration and derivation, and they do all these approximations to be able to step ahead. And so the recommended values were below 50 milliseconds for each time step, and I just put it to 10 just to be sure.
Looking at your system architecture, I mean, that resembles a normal state machine, but you didn't create the states by hand, did you?
So,
okay. I mean, normally I'm used to a state machine, you feed it inputs and it decides what the next state will be. This looks a little bit like it, but a little bit different too. Can you sort of elaborate on that?
Yes. So it is a state machine, but your state's defined. Your state is completely defined. That's what I would say.
The state is just a snapshot at one of these 50 millisecond intervals?
Yes.
Okay.
State is just a snapshot, and it's only a snapshot of certain components of those intervals.
Right.
So, for example, the lander, it's a snapshot of the angle, which is absolute value angle x plus absolute value angle y, log 2 position z, log 2 velocity z. That's just your state. And if between simulation steps that doesn't change, it means that you don't really realize that you've moved. So until you don't change, you won't generate a new thrust. And you're going to continue executing the same thrust until you find yourself in a new state, at which point you're going to do something different.
Okay, one more question. In really doing this, the fuel load and the center of gravity would make a huge difference to the performance. Have you considered that in this model, or is that something for the future?
That's a good point. Right now I'm taking, so OpenRocket allows you to build your own rocket. You can drag components here and there. I used one of their built-in hybrid rockets, and I did not consider taking in the center of gravity. That would be interesting. And one of the critical things here is also this approach doesn't calculate the physics of the problem. It solves the problem without calculating the physics. Because using control theory, and so potentially doing some, it might be useful to know where my center of gravity is, because if I'm losing thrust, then I'm using the thrust, I'm losing mass, so that might be useful, but I wouldn't be able to still simulate ahead in time. Like the rocket itself currently doesn't, and probably wouldn't have the CPU capability to be able to simulate ahead in steps, unless you have a very powerful controller on the rocket. So the idea is it's a very dumb controller. You train it a bunch in the simulator or in the real world. You train it, and then it just knows what the best thing is to do. It's not able to see ahead in the future and predict what's going to happen.
Okay. And in your model, you didn't really care where it landed as long as it just landed.
That was the idea. I'm still working on the reacher component, which is not there yet. And so I had some results, but they weren't nearly as good. So I just need a little bit more time for these. But yeah, I think I have pretty good faith. The video I showed all of you, it went a little bit left and right, and then you could see that at the end it went towards the center. Now that was actually a video of of me using the reacher, but it came out to be a good video. Yeah, the idea is
actually see the video.
This. I'm sorry.
I couldn't actually see the video. I don't know if others.
Okay.
It looked green, but I could see the little rocket coming and landing.
Yeah, that's one of the difficulties, because I also have it on my phone. I'm gonna try again, so I'm actually gonna put it on my camera feed, if that's okay.
So just to note, we've gone about 20 minutes, so that's what the other groups had. So I don't know if the judges want to end it now or continue discussing. I'll leave it up to the judges, but I just want to note that this is the same time the other groups have had.
Okay, got it.
One more question.
Yes.
Old school, when we used to do this sort of problem in the analog world, we always learned that first derivative wasn't enough. You had to go to second, and sometimes third. Is that same concept embedded here in the learning process, or how do you handle the other dimensions of stability?
There's a good point. So I would say that going to another derivative, for example, the landerize position velocity, going down to acceleration would be extra, because it's already choosing the acceleration, right? That's one of the parameters it's selecting, is the thrust, which is going to then drive the acceleration. So it was important for the stabilizer to have the angle velocity as part of what it knew what to do. The angle and the angle velocity to be able to stabilize correctly. Also, it's just a proportional controller, right? If you only have angle, and then proportional derivative when you have angle velocity, which is pretty good. And it performed very, very effectively with angle velocity. Without angle velocity, it was actually not as good. So it did get better with the derivative.
Okay, great.
If you have a sneak at my camera really fast, the video of before, I can I'm gonna replay it really fast. Okay.
Right. There we go.
It's a little difficult to see because I'm trying to mirror the video.
Yeah.
Yeah. See, it's it's coming in for a landing.
And the thrust is the blue thing.
Yeah.
So. Okay, perfect. Yeah, because I showed this video before, and that way.
Yeah.
Yeah, I'm sorry I'm showing it on a phone, and
Very good. Thank you.
Perfect. Thank you very much then for this. This was fun.
Yeah, thank you, Francesco.
Yeah, thank you.
Perfect. Have a wonderful day, and best of luck with the rest of it.
Thanks.
Very good. Thank you.